Hydrolysis. There is a total of 5 hydrolysis reactions and 7 equations that we're going to look at. First one we're going to look at is your acid chloride. So acid chloride can undertake hydrolysis in the presence of water as well as alkaline as well. Of course, in the case of alkaline, we end up with carboxylic ion. Halogenal alkane can also undertake hydrolysis, but that will be partial hydrolysis because water is not such an effective nucleophile. Certainly, you can add alkaline and enable a faster nucleophilic substitution rate that will also produce your alcohol as well. The next 3 are the one that we'll be spending time to focus on, which will start off with ester, followed by nitrile, and then your amide. And why earlier I mentioned 7 equations, because you have your primary amide, secondary amide, and then your tertiary amide. When you actually have an acidic medium and an alkaline medium, in the case of ester, you will find that you need to take note that carboxylate ion in alkaline medium, you will end up with carboxylate ion. And if the alcohol happens to be phenol, then your phenol can neutralize as well to form phenoxide. And before we go further to look at the products that's formed for acid hydrolysis and alkaline hydrolysis, I want to highlight the fact that in acid hydrolysis, actually H+ behave as a catalyst. So for example, in the case of carboxylic acid, in the presence of H+, the carbonyl group, or specifically the oxygen in carbonyl group, will act as a base to accept the proton from the H+. Consequently, you will find that with this electron transfer, the carbon in your carboxyl group becomes C+, and of course your oxygen binds with H+ to form your OH. And certainly in doing so, we know that the carbon in the carboxyl group has become C+. And it becomes C+, you will find that you will better able to attract the water molecules and bind with it and to initiate the nucleophilic substitution reaction. In a nutshell, during acid hydrolysis, H+ is a catalyst and not a reagent. So in the case of alkaline hydrolysis, the nucleophile is in actual fact OH- because OH- is negatively charged, which means it is a more effective nucleophile than your water molecule. So the OH- will be attracted to the carbonyl group in your ester, and consequently nucleophilic substitution occurs, allowing you to produce your carboxylate and your alcohol. So that is the key difference between acid and alkaline hydrolysis. So similarly, in the same vein, if you're looking at the acid hydrolysis of your amide, and specifically in this case is a secondary amide, you will find that the H+ will still act as a catalyst, and there will be a transfer of electron for you to produce this C+. So water molecule remains to be the nucleophile. In an alkaline hydrolysis, for this example, which is a primary amide, you will find that the OH- will be the nucleophile instead of your water molecules. So with that, we can conclude this. In the hydrolysis of ester, you can actually cleave the bond between C double bond O and the O. And in this case itself, you can then add the OH here, where the other H will be added to the oxygen to give you your alcohol. So this is obviously the water that you added, allowing you to produce essentially your alcohol and your carboxylic acid. And clearly, if it is acidic hydrolysis, both alcohol and carboxylic acid will not undertake any neutralization because both are acid as well. So the products are as such. However, in the case of an alkaline hydrolysis, then what you do get is that you need to note that your carboxylic acid definitely will be neutralized. In the case of alcohol, no neutralization will occur. However, if the R prime happens to be phenol or the benzene ring, then in this case, you will get your phenoxide. If the R prime, as I mentioned, is actually a benzene. And as far as amide is concerned, what then happened is that you could also cleave the bond between C double bond O and your NH. And in the same vein, you add your OH molecules to carbon and add your H to your nitrogen. And so the H2O is added to your amide as such. And clearly, if let's say it's an acidic hydrolysis, again, in the same vein, your acid is acid, your carboxylic acid is acidic, while your amine is a base. So your amine in this case, if happens to be primary amine, must accept the H+ to form your quaternary ammonium salt. In the case of alkaline hydrolysis, carboxylic acid will be neutralized to form your carboxylate, but your amine, which is a base, will not react. So with that, let's take a look at some equation writing. Let's start off with ester. So in the presence of the hydrolysis of ester, take note it's an irreversible reaction, and H plus is right at the top because it's a catalyst. While in the case of the alkaline hydrolysis, your OH minus is a reagent, so it's not actually a catalyst, and there's no catalyst that's present. And the NaOH minus is a reagent. You end up with a carboxylate and not a carboxylic acid. Next, let's take a look at the hydrolysis of nitrile. In the case of hydrolysis of nitrile, in fact, the reactions that take place in the hydrolysis of nitrile can be summarized here. The nitrile will first convert itself to actually your primary amide first. How it does that is that it actually cleaves some of the bond here, and then the oxygen binds with the carbon, and 2 of the hydrogen binds with the nitrogen. That's how the H2O is added to actually your nitrile. So in the first step, what happens is that your nitrile is converted to primary amide. Then the primary amide then undertake hydrolysis to produce your carboxylic acid and your ammonia in this case. And given that it's an acidic hydrolysis, ammonia is a base, and therefore it will be further neutralized by the H plus, and this is your final equation. In the case of alkaline hydrolysis, the same thing still occur. You add the water first to produce your primary amide. The primary amide undertake hydrolysis to produce your carboxylate and your ammonia. It is carboxylate, since carboxylic acid that's produced is neutralized by the OH minus in the alkaline medium. Finally, let's take a look at the hydrolysis of amide. So in the hydrolysis of amide, if it's acidic hydrolysis, this is what you get. And in alkaline hydrolysis, this is what you get. If you actually were to hydrolyze your 2-degree amide, say for example, this reaction, these both are the respective acidic and alkaline hydrolysis. In all cases, it's quite clear. And similarly, in the 3rd-degree amide, if you were to use that as an example, these are the products that you get. Consistent in all these examples, what we want to highlight is that if it's an acidic hydrolysis, then you can clearly see all the amine that is produced will be neutralized, as underlined in purple. While in the case of alkaline hydrolysis, then it's clear that all the carboxylic acid that is produced will now have to end up as carboxylate, because the carboxylic acid is acidic, so it has to be neutralized. And finally, in the last part of hydrolysis, we will be running through acid anhydride, which certainly is not in the A-level syllabus, but extensively asked in exam questions. So before we do that, I think it's good for us to have some understanding that in terms of nucleophilic substitution and in terms of leaving group, this bond energy is the weakest, making your acid chloride the best leaving group. Following on to that is this group, your acid anhydride, and then your ester, and then followed by your amide. So bear that in mind. So let us now zoom into acid anhydride. In the hydrolysis of acid anhydride, if we were to look at this example, there are 2 possibilities. We certainly could have this going this way, and in the process itself, you can have this compound formed in this manner, which means you'll produce your ethanoic acid, and this will be this will then be your propanoic acid. However, we also need to note that actually this carbon, which is also delta plus, could also be attacked by the nucleophile in this fashion. You won't produce your propanoic acid in this manner, and the other one will end up as your ethanoic acid. So you end up basically the same product actually, all right? So you end up with actually the same product. Let's take a look at what happened now in the case of acid anhydride. Say you were to react with alcohol, say for example, methanol. So in this case, as sketched in red, you'll find that basically there are 2 possible ways now you could undertake the reactions. In the first way, this is what then happened, which means you will end up with propanoic acid, which is this one, and your methyl ethanoate, which is the one right at the top. The other way is if the oxygen were to attack the carbon, the lower carbon in your acid anhydride, then in that case, you will find that the H will then have to join with the rest of the other groups, which means you end up with ethanoic acid and your methyl propanoate below. So you end up with actually a range of 4 different organic products.